First half is good. You don't need to do all that.
Okay.
Just tell me
Now
what's the
let's-
function being differentiated by this.
You're always like,
You're not. What? Today's lucky, so I'm tired.
Thank you.
dude, I was so
Thank
close
you.
to taking Brit.
Thank you. Can you let me ask please?
You
Thank you. All right. So with number this one, what's the slope way out here on the left? And then what's the slope right here, -1? Zero. So we have negative slope and then zero slope. And then what's the slope between -1 and +1? Positive. And you're getting progressively more positive in your slope. So you do something like this. And then what's the slope right there at the sharp turn? Nope. Doesn't exist. It's not like here where the slope is getting progressively less negative gradually and then slowly getting positive. So there's like a gradual change in the slope from negative to positive where we pass over a slope of 0. The curve is like actually flat right there. The curve isn't flat up the sharp turn. The curve is getting more and more and more positively sloped, and then suddenly the slope is negative. So there's no like gradual shift from positive slope to negative slope. It's a sharp, boom, turn. And so the derivative just gets cut off and then jumps down to a negative slope. What shape is this thing? A line. So what's the slope of this line? You have a couple of points. Yeah, the slope of that is -1. So you're down here at a height of -1, the entire right side of the graph. I'd accept that. If you don't understand this thing as being a parabola, if you kind of read this as being something other than a parabola, then you could make the argument that the slope here is kind of approaching positive infinity, and then this would be a vertical asymptote that you're approaching, and you can do that with your F prime. So I would accept either the line getting cut off and then a flat line, or if you have this kind of morphing into a vertical asymptote from the left and then jumping down here, both of those are fine. The key thing is that you're negative until x equals -1, the slope is 0 there, and then you're positive, and then you jump down here to a slope of -1 on the right side of the graph. For number this thing, block 2, what's the function here being differentiated? All right, so this first half of the numerator tells you the function, and this is 3, that's in the place of x, minus 2 in the place of x, and 3x squared minus 2x. And at what value, what's our c? 1. So it's like c plus h is 1 plus h here. And then if you wanted to evaluate the limit, you wouldn't actually do the limit, you would do the derivative and plug in 1. Same thing here, but now instead of the standard definition of the derivative, now we're using the alternate definition of the derivative. What's our function? Yeah, so again, the first half of the numerator tells you the functions. This is 3 over x plus 1. And what's our c value here? So the limit and the denominator tell you what that is. And again, if you wanted to find out what is the value of the limit, you would wait a couple of weeks until I've told you how to differentiate this, and then differentiate that and plug in 7. Because that's what this limit represents. So again, you'll have a couple of these things, maybe not to this level of difficulty on the quiz, and then you'll have something like that on the quiz, in addition to being able to, just do your derivatives and stuff. We've also been doing all the homework. Get out the homework. Is there anything that we want to look at from those problems? The last one, which was 63? 97. Oh, yeah, the word problem. All right. So 97. We drop something off the building. The thing did not match?
Yeah, the answer key.
Did not match what? What was number 63 on the answer key? X plus cosine x?
I think thing. Hold on.
Oops. All right, so it's a good thing we're going over it then, huh? So x plus sine x from 0 to pi. It's my 63.
It's 63.
And we want when points, when tangent line is horizontal. And then 97.
Yeah, 63 match.
Yeah, okay, so no roast candy. That's fine. Who wants 63? Right, go ahead, Iman. And who wants 97? Prince, welcome back. You can have 97.
What if I do A, B, C, D?
You
Oh,
want
yeah,
to do
I didn't know E either, but I had another
What's E?
question.
Oh, okay. How about two of you work together? Oh, you want 61 up here?
No, yeah.
So that you can do it?
No,
Oh,
I
okay,
can
so
do it.
Yeah, so we'll put up 61, and Prince and Laura, you guys can tag team 97. You divvy up among yourselves who does what.
I don't know how to do party structure things.
Yes?
Okay, problem first thing. Second thing. Board points.
Yes.
If all of them except for E.
Oh, I choose.
Raise your hand.
So what about board points?
Hand up.
At
I
2?
don't like that.
For hands up? What, you don't like this?
No, I don't like how like I'm in it. It's weird. No, I'm fine.
You have your hand up?
No, it's an E.
Who? Sorry. Tanika, you got a board point. We'll get you again sometime, like tomorrow. Unless I know I can get this conversation. And then I won't. I'm sorry. I legitimately am not seeing you again. I don't know why. I'm farsighted. Maybe that's why.
Just in your eyes while you're raising your hand.
Um,
I go straight above you because I witnessed it happen.
that the G is being loud or? That's a Oops.
Your handwriting is like so satisfying.
Who did this? So when you say sine x equals cosine x, is what you mean the derivative of sine is cosine? Okay. So that there's not confusion that we think that sine is the same thing as cosine. Risa? What? So did you write dy dx here? So y prime equals d dx of all that stuff. And then you wrote 1 plus cosine x, like that. I do want to, so like you should label your final equation as y prime. So you should have like y prime equals 1 plus cosine x. But like this isn't wrong. And this is good notation of saying the derivative of that stuff. So who, Iman, talk to us. Rachel, go.
I was going to say, is there
dy dx means the derivative of y. So dy dx is analogous to y prime. D over dx is like the derivative of something, and then you would put the something that you're differentiating in brackets after it. So this means we're taking the derivative of this stuff, and that's what we get. Whereas dy dx is the derivative of y. Iman, talk to us. All right, real quick. Solving this equation, cosine of x equals what? How do you get the 1 over here? -1, which is why the angle is pi. Because cosine of pi is not 1, it's -1. So, but yeah, you got to subtract the 1 over, so it's negative. So you're actually good. So you have your x coordinate. Once you got that, we want the point. Plug that back into the y function, and that's beautiful. Any follow-up with 63? Raisa? Yeah. Prince? I can do that. All right. 61, similar idea. Rachel, talk to us. Not Rachel. The person who did 61. Thank you. You. Sorry. Grace.
You make the 1 over x squared x to the negative second, and then you do the derivative of that. Oh wait, I forgot the x. And then you put it back into the denominator, and then you set it equals 0, and then you can't, and then it's imaginary, so there's no.
Well, it's not even imaginary. Like, this is so bad, you don't even get an imaginary solution. Like, if we were going to try to solve this equation, what would you have to do to try to solve this thing? Yeah, multiply by x to the third. And that leaves us with what? 0 equals -2. That's just no. So that's why we don't have a solution here. Sometimes you might get an imaginary solution. We saw that yesterday. In this case, we don't even get that. We get really nothing. So, but the end result is, you're right, there are no tangent lines that are horizontal to that curve. Any follow-up on 61 or 63, or this general idea of finding points where tangent lines horizontal, Prince?
Where y prime and then the pi equals pi plus sine pi, right? That whole line. Why is it y prime instead of no? Yeah. Why is that y prime instead of y?
That's a good point. It should not be y prime. So y prime is the derivative, and that we set equal to 0. Once you've got your x coordinate, we're finding out y. So this is y of pi, and that's the y equation. So this isn't y prime, this is just plain old y. Good catch. Anything else? All right, 97. Prince, talk to us. Okay, so first of all, we have a silver dollar, and we're going to go up to some building, and are we dropping it or throwing it? Dropping it. So our generic form is what? -16t squared plus v naught t plus s naught. And how did you come up with this equation? Like, where's my v naught t term? I don't see it.
Oh, I wrote that down.
So what do we do with the dollar?
You just, there's no initial velocity, so like, initial velocity is 0, so that's what it cancels out.
Okay.
S, and we're out 1,360 feet, so that's that S naught. And then, negative 16
All right, so we have our position and velocity equations there. Any questions with building those? Because we got to have those clear before we can do anything else, right? So, why isn't this negative? Because that's our initial height, and we are not 1,362 feet in the ground. We're up high, that many feet above the ground, so that's positive. So negative indicates up or down. Negative would indicate down. Negative position is below ground. Negative velocity means you're moving down. And negative acceleration means your speed is, your velocity is getting more negative over time. So no initial velocity means it's 0, but that's because we're above the ground, that's positive. Any other questions with part A? Part B, we jumped over here for some reason. Okay, so Laura, in part B, we're finding the average velocity over this period of time from 1 second to 2 seconds. Tell us what you did.
So I did this one formula that was S2 minus S1 of prime. What that I've given. And then so I plugged 2 back into this equation we got in part A. And so, you know, you get that number, 1,000, whatever.
Yeah.
They get the other number by plugging 1 in. Okay. And then math, you get negative. Okay.
48. Is that the only interval we wanted? Oh, and she's showing how did she get these two numbers right here. So that's nice of you to show us that. Back to C. Prince, what are we trying to find out in part C? So in part B, we want the average speed, the average velocity over this period of time from 1 to 2. In part C, we want the instantaneous velocity right at second 1 and then right at second 2. So to get that, what did you do? In the B equation, not your S equation. So you're using the derivative equation from part A. And then in part D, we want to find out how long until the dollar hits the ground. Yeah. All right, so when the dollar hits the ground, how high is it? So we set the position, where it is, equal to 0, and solve, and you got that. You guys can do the math once you understand position equals 0 is when the dollar hits the ground. And then in part F, somebody did physics. Who is part F? Or E? All right, Risa. Yeah, so you have a velocity equation way back from part A. We want to find the velocity when the dollar hits the ground. We now know the time when the dollar hits the ground. We just did that in part D. So we put those two things together, take the time it takes to hit the ground, put it into your velocity equation that you already found, and that's your velocity at the moment of impact. Any follow-up with this? Yes. Part D, because we're trying to find the average rate of change of position. That's what velocity is. So velocity is the change in your position over time, and the average rate of change is then going to give us the average velocity. So that is the slope. So the slope of S is V. That's why S prime is V. And since average rate of change is the slope over a period of time, you're doing the slope of S to get your average V over that period of time. Dice say rows 2 and 3. Yes. What's up? So, you did number 6. So, root 3 times x. So x is not. So the derivative of that would be root 3 is your coefficient on x. It's like root 3 times x. The second half is fine. So that would be root 3 minus 2 sines. And that's actually plays pretty nice. Alright, go to. The rest of you is look over there, start thinking about 66. We're going to do 2 of those together, or we'll do 1 together and then I'll have you guys try one for yourself. You have these on your homework tonight. And then I want to go back and do a little bit more with word problems. Do I have an eraser? Is that bugging you again? What is it? All right, what's that about? Oh, that's the other people who sit there are high school boys. So.
I know, but I don't want
All right, so these kind of problems, they're a little tough. K is some constant that we're trying to find out. We don't know what it is. And what we want to do is find out what does K have to be in order to force this line to be tangent to this function somewhere. So we're going to find out K. While we're at it, we'll also go ahead and find out what is that point. Where is the somewhere that this line is going to be tangent to this curve? And in order to do this, you really need to fall back on 2 things. And I'm going to keep hammering on this. Y is f of x, and m is f prime of x. So when you see f of x, just think, oh, that's just fancy y. And when you see slope, just think, oh, that's just a derivative. Derivatives of slopes, and y is f of x. Those are the same thing. So what we're going to do is end up creating 2 equations based on these 2 facts, and use that to then basically have a system of equations that we can solve for k, and also while we're at it, we'll find x just kind of incidentally. So maybe what should we do with f of x? What would be a good start? Find the derivative. When in doubt, find a derivative. So we know we're going to have to use f of x at some point and its derivative. So let's go ahead and get its derivative right off the bat. So what's f prime of x here? What's the derivative of k? Nothing, because k is a constant, not a variable. So k goes poof, he's just a constant term. He's not attached to any x. What's the derivative of negative x squared? Negative 2x. So now we have our derivative. What piece of information should we extract out of our tangent line? So we could think of this as like going to equal f of x. So y is f of x at some point. With the line, now that we have a derivative, what do we want to do with our derivative? Set them equal to what? Not y. Derivatives are not y. Derivatives are slopes. What's our slope? So we come over to the tangent line and we say, hey, we can get a slope of that. Slope is -6. So you have a function, get its derivative. You have a line, get a slope. And then use that fact that derivatives are slopes and set these equal to each other. So I'm going to come over here and say, oh yeah, derivatives are slopes. So -2x equals -6. Now you might look at that and say, well, how does that help me find out k? There's not even a k in that equation. How am I going to find k? Well, maybe we need to find x as a stepping stone to finding k. So what's our x value here? 3. All right, so x equals 3. Bah, 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 bah. So now we've solved for something. We didn't solve for k, which is what we want, but at least we solved for something. Maybe we can use that in our quest to find out what k is. So now that we've got that, we can come over here and we've used up derivative and slope. What haven't we really used yet at all? Y or f of x. So let's use those. We have an equation for y and we have an equation for f of x. If this curve is going to be, if this line is going to be tangent to this curve, that means they have to intersect somewhere. And where are they going to intersect? Where are they going to intersect? When x equals 3. So you know that y is f of x. You have an equation line with y. You have a function with f of x. You can use them, set them equal. And then you know they're going to equal when x is 3. So we can come over here and say y equals f of x. And say, well, y is the same as -6x plus 1. And f of x is the same as k minus x squared. So this is now basically doing a system of equations, and you're substituting what you know about y from the line and what you know about f of x from your function. And then you can keep on substituting and plug in what you know about x from what you solved with the slope derivative equation. So when you plug 3 in here, what do we get? -18 plus 1 equals k minus 9. And now you can solve that for k. So what is k going to be? -8. Go with -8. Ta-da! So you got your k value. Now, I said, while we're at it, let's also get the point of tangency. The point of tangency is in x comma y. We have our x. How can we find our y? Yeah. And we can plug that into either the function or the line. It won't matter because when x is 3, these guys are the same. We use that fact to find out k. So I would probably just plug x into the line equation to find the point of tangency, and because the line equation is already kind of set. So point of tangency, y equals -6 times 3 plus 1 is what, -17? So point of tangency is 3 comma -17. And that's the point of tangency for this curve with that line when k is -8. So there's a lot of moving parts here, and it's easy to lose track of stuff. But if you always fall back on y is f of x, and if you have a line and a function, there's your y and there's your f of x, and derivatives are slopes. A line gives you a slope, and you can always find a derivative. Any questions with any pieces of this? Raisa? Yeah. So general steps. Find f prime of x. Find m. Set f prime of x equal to m. Maybe solve for x. You might not be able to solve for x. So there's going to be situations where your derivative still involves k, and you have derivative in terms of both k and x, and then things are a little messier. So if you can't solve for x, then also set y from line equal to f of x equation. So we do what we did over here of set your y stuff equal to your f of x stuff. And then you substitute. Probably for x and solve k. In that equation. So maybe instead of calling that step 5, that's like part of step 4. So in step 3, if you can't solve for x and get a value, maybe you can solve for x in terms of k and have like x equals some expression of k that you could then plug over here and solve for x. You might need to do it the other way around, bless you. But usually your derivative is a simpler equation than the function. So probably you want to work within the derivative, isolate x, and then substitute that over here, whether it's a value like we did, or an expression involving k. You can substitute that over here and solve for k, and then you're in good shape because you have your k value, which is really what you're looking for. So here's 68. It's the same prompt, but a different set of information. So 68, same as 66, but now f of x equals k root x, so k times square root of x, and your tangent line is x plus 4. So you guys go ahead and try that. And you can race me, because I'm doing this for the first time. Don't worry about finding the point of tangent. Just get k. And you should find out 2 separate values for k. There's 2 answers that work. Yep. No, wait. There's k. K is a multiplier. K is part of your coefficient. So it's k. So this k is not a constant term. K is a constant multiplier. It's a coefficient. So it is multiplied by 1. So yeah. Yeah. So you have to do it. Yeah, so that.
So,
All right. What is f prime of x?
It's x plus 4.
Thank you. What's f prime of x? Okay, rewrite f. I don't want to hear I don't know. Think. So how can we rewrite this? Power rule. What do you do with the 1/2? Multiply it. What do we have up front now? And then x to the negative 1/2. So the k is just a constant multiplier. It's a coefficient. So you can then rewrite this. What's in the numerator? 1 times k is k. What's in the denominator? 2x to the 1/2 or 2 root x. So there's f prime of x. Now what do we do with f prime of x? Set it equal to m. So what's our m? 1. So we have our m and we have our f prime, and we set them equal to each other. So we can say f prime of x equals m, so k over 2 root x equals 1. Can we solve and get a value for either k or x right now? Can we get a value, like a number solution? No. Can we isolate k though? So let's at least isolate k. So if we get k by itself, how do we do that? Yeah, multiply 2 root x over here to both sides, and you get k equals 2 root x. All right, let's box that and say, we don't know what k is, but we have it in terms of x. Now, a lot of us are getting here just fine, or muddling through here, and sort of, and then they're not using at all the other equation. So there's 2 pieces of information you got to use. You got to use derivatives or slopes. You also have to use y is f of x. We've got to make use of that. So over here, we're going to make use of f of x equals y. What's f of x? K root x. And what's y? X plus 4. It's fair game, I taught it. Now, this is a hell of a lot harder than the first one, right? Yeah, this is, so these are not all created equal. Some are not so bad. This one's considerably worse. Now that we have 2 equations, we can do substitution. This is a system of equations. You did systems of equations in Algebra 1. This is a lot more heavy of a system of equations, but the general rule of substitution is still the same. You know what k is. Substitute for k, so you have 2 root x times root x equals x plus 4, and now you can solve for x. What's root x times root x? X. And now you're on your way. So now you can solve this for x, and then back substitute over here and find out k. Yes. Don't tell me no now. You can solve this. That's easy. No, it is. 2x plus. You'll say this. I'd be upset with my Algebra 1 students if they say, no, I can't solve that.
I'm not saying that.
Oh, the whole thing?
Yeah.
Fair enough. The ones on homework are not done. This one's evidence. Oh, why not?
Just make it more summary.
No.